Welcome to today's problem walkthrough. We'll be tackling LeetCode problem number 174, Dungeon Game. This is a challenging problem that tests your understanding of dynamic programming and pathfinding algorithms. Let's dive into the problem and explore how to efficiently solve it. The Dungeon Game problem places a knight on a mission to rescue a princess who is held at the bottom right corner of a dungeon represented as a 2D grid. Each cell in the grid contains an integer, which represents the health points the knight will gain or lose upon stepping into that room. The knight begins his journey at the top left corner, at cell 0, 0, and must make his way to the princess at cell M1, N1. However, he can only move either right or down with each step. To successfully complete his mission, the knight must maintain a health level of at least 1 at all times. This means we need to determine the minimum initial health the knight must start with to ensure he can clear the dungeon and rescue the princess without his health ever dropping below 1. To solve the problem, the output we are looking for is a single integer, which represents the minimum initial health required for the knight to complete his journey while staying alive. Let's consider an example. For the input grid shown, where the dungeon contains values like -2, -3, and 3 in the first row, followed by -5, -10, and 1 in the second row, and finally 10, 30, and -5 in the last row, the minimum initial health required is 7. This ensures that the knight can navigate through the dungeon without his health dropping below 1 at any point. In the given example, the knight starts with an initial health of 7 and follows the path from the top left to the bottom right corner, first moving down to 1, 0, then to 2, 0, next to 2, 1, and finally reaching 2, 2. Along this path, the knight encounters both health losses and gains. Starting with 7 ensures that his health never drops below 1, allowing him to survive. In another example, where the dungeon grid is smaller, such as a 1x2 grid with values 0 and -3, the minimum initial health required is 4. By starting with 4 and moving right, the knight's health remains at least 1 at all times. For a single-cell dungeon grid like 3, the knight only needs the minimum health of 1 to rescue the princess, as this cell has a positive value. This means the knight does not face any health loss along the way. Now, let's look at the constraints of the problem. The grid can have up to 200 rows and 200 columns, and the values in each cell can range from -1000 to 1000. These constraints mean that we need an efficient solution capable of handling larger grids with mixed values, as well as scenarios involving both positive and negative health effects. There are a few edge cases to consider. For the smallest grid possible, a single cell with a positive value requires a minimum health of 1, while a single cell with a negative value means the knight must start with sufficient health to survive the negative effect and still have at least 1 health remaining. Similarly, in a dungeon where all cells contain negative values, the knight must start with enough health to survive all negative points in his path. On the other hand, if all cells have positive values, the knight only needs the minimum health of 1. For larger grids with mixed values, the solution must efficiently calculate the optimal path and determine the exact health required to ensure the knight's survival throughout the journey. To solve the dungeon game problem, one possible approach is the brute force method. The intuition here is to start at the top left corner of the grid and explore every possible path to the bottom right corner using recursion with backtracking. At each step, you calculate the minimum health needed to move to the next cell, ensuring that the knight's health never falls below 1. However, this approach comes with significant drawbacks. The time complexity is exponential, 2*m*n, because it evaluates all possible paths without leveraging any optimizations. Additionally, the space complexity is O(m*n) due to the recursion stack. Ultimately, this method is infeasible for larger grids as it doesn't take advantage of overlapping subproblems, making it highly inefficient for practical use. An efficient alternative is the dynamic programming approach, specifically a bottom-up method. Here, instead of solving the problem from the top left corner to the bottom right, we reverse the process. Starting at the bottom right cell, where the princess is located, we work backwards toward the top left. At each step, we calculate the minimum health required to move forward, whether to the right or downward. This ensures that the health required to survive is minimized at every step. A key observation is that the health needed at any cell depends only on the cells immediately to its right and below. For example, at cell I(j), the health required is determined by the formula max 1 min health I plus 1 j health I j plus 1 dungeon I j. The max 1 component ensures the knight's health never drops below 1. To implement this, we use a dynamic programming table where health I j represents the minimum health required starting from cell I j. By filling this table in reverse order, from the bottom right to the top left, we can efficiently determine the solution. This approach has a time complexity of O(m*n) and a space complexity of O(m*n), making it both efficient and practical for larger grids. The bottom-up dynamic programming solution can be further optimized by reducing its space complexity. Instead of maintaining an entire MXN table, we only need to store the current and previous rows or columns to calculate the results. This reduces the space complexity from O(m*n) to O(min)(n), depending on whether we iterate over rows or columns. To implement this, we use a 1D array to represent the health values for the current and previous rows. Despite this optimization, the time complexity remains O(m*n), as we still process every cell in the grid. This space-optimized approach achieves the same results as the full DP solution but uses significantly less memory, making it ideal for scenarios where memory usage is a constraint. It strikes a balance between efficiency and practicality while maintaining the robustness of the original DP method. The chosen strategy for the dungeon game problem is the bottom-up dynamic programming approach, specifically its space-optimized version. This method is efficient, with a time complexity of O(m*n), and avoids the exponential blow-up associated with the brute force approach. It guarantees an optimal solution by leveraging overlapping subproblems and solving them in a reverse order, starting from the bottom right cell. While the full DP approach is robust, it uses more memory than necessary, which makes the space-optimized version a better choice. The trade-offs between the approaches are clear. The brute force method is intuitive but impractical, the full DP approach is efficient but memory-intensive, and the space-optimized DP method provides the best balance of performance and memory efficiency. The key insight, or aha moment, came from recognizing that working backwards simplifies the problem significantly. By calculating the minimum health needed at each step based on the cells to the right and below, the problem transforms into a manageable dynamic programming challenge. Ultimately, the space-optimized DP approach is the recommended solution for its optimal balance of time and space efficiency. To solve this problem, we aim to determine the minimum initial health the knight needs to survive while traversing a dungeon grid. Each cell in the grid represents a gain or loss in health, and the knight must reach the bottom right corner without their health dropping to 0 or below at any point. The brute force approach starts by defining the problem recursively. At any given cell, we calculate the minimum health required to move to the next cell, either to the right or downward, while ensuring survival. The base case occurs when the knight reaches the bottom right cell. Here, we calculate the minimum health required to survive that specific cell. If the value in the cell is negative, we subtract it from 1 to ensure survival. Otherwise, if the cell has a positive or 0 value, the knight needs at least 1 health to proceed. This recursive process captures the essence of exploring all possible paths through the grid. Now, from any cell, the knight has 2 possible moves, they can go right or downward. For each option, we compute the health required to take that step. The health required at the current cell is determined by the minimum health needed for the next step, adjusted for the value of the current cell. Specifically, we calculate the minimum health between moving right or down, and then subtract the current cell's value. To ensure the knight always has at least 1 health, we use the max 1 function. This ensures survival even when encountering a cell with a large health penalty. The brute force approach evaluates all possible paths from the top left to the bottom right, keeping track of the minimum health required along each path. However, since this approach explores every possible path, it results in an exponential time complexity of O(2)m plus n. Finally, the result of the recursive function at the starting cell gives us the minimum health required to begin the journey. This approach highlights a key insight: the health required at each cell depends on the worst-case path from that cell to the destination. However, one major inefficiency in this method is the overlap in recursive calculations. Many subproblems, such as evaluating the paths from the same cell multiple times, lead to redundant computations. This redundancy significantly increases the time complexity. To address this, we can optimize the solution by switching to a dynamic programming approach. Instead of recalculating the result for each subproblem, we store the results in a table and reuse them. This eliminates the need for repeated evaluations, greatly improving efficiency. In terms of data structures, a recursive stack is used to keep track of the state for each call. However, as the grid size grows, this can lead to stack overflow. Additionally, the input grid itself plays a crucial role, as it determines the health gain or loss at each cell. This forms the foundation for transitioning to a more efficient solution. The recursive approach involves several key operations. Each recursive call evaluates the minimum health required to move to the next step, while the base case handles the specific scenario when the knight reaches the bottom right cell. At each cell, maximum and minimum calculations are performed to ensure survival. The max, 1, ensures the knight's health never drops below 1, while the min helps identify the optimal path requiring the least health. To optimize this further, we use a dynamic programming approach. By building a DP table from the bottom up, we can iteratively compute the minimum health required at each cell. This avoids redundant calculations, dramatically improving efficiency. Additionally, we can optimize space by using a single row or column instead of a full DP table, reducing the space complexity from O(m*n) to O(min)(m)n). This combination of iterative computation and space optimization significantly enhances the solution. When optimizing, it's also critical to handle boundary conditions effectively. For example, at the last row or column, the knight only has one possible movement option, and the calculations must account for this constraint. To visualize the problem, think of a knight navigating a grid where each cell represents a decision point. The knight must evaluate whether moving right or down will require less health, while ensuring they never run out of health. Recursive calls simulate this decision-making process for every possible path. In the brute force approach, this exhaustive exploration leads to inefficiency. However, by switching to dynamic programming, we eliminate redundant computations, storing results for subproblems and reusing them as needed. This transition from brute force to DP transforms the process, making it far more efficient while maintaining the accuracy of the calculations. This implementation solves the dungeon game problem using a dynamic programming approach. Let's break it down step by step. 1. Initialize variables. The dimensions of the dungeon grid are determined using len, dungeon, for rows, m, and columns, n. A DP table is then initialized with dimensions, m+1 x, n+1, and filled with float, inf. This is to handle out-of-bound references gracefully. 2. Base case. The minimum health required at the bottom right cell of the dungeon, goal cell, is set to 1. This ensures the knight survives even if the cell has no health reduction. The auxiliary boundary cells DP, M, N1, and DP, M1 is yen, are also set to 1 to facilitate the calculations. 3. Filling the DP table. Starting from the bottom right corner, just before the boundary cells, the table is filled moving upwards and leftwards. At each cell, I, j, the minimum health required to proceed to the next step is calculated as the smaller of the values in the cell below, DP, I+1, j, or to the right, DP, I, j+1. This value is adjusted by subtracting the health effect of the current cell, dungeon, I, j. If the resulting health is less than 1, it is capped at 1 to ensure the knight survives. 4. Result. The value in the top left cell DP, 0, 0, represents the minimum initial health required for the knight to successfully traverse the dungeon. This approach ensures efficiency with a time complexity of O(m*n), where m and n are the dimensions of the dungeon. By working backward from the goal, we ensure that each cell is processed only once, making this solution optimal for grid-based problems like this. Here, we begin by importing the necessary Java utilities and defining our solution class. The key function is calculate minimum HP, which takes a 2D array representing the dungeon as input. First, we determine the dimensions of the dungeon matrix, M and N. Next, we create a dynamic programming table, DP, to store the minimum health required at each cell. This table is initialized with a large value, essentially representing infinity, to ensure that unprocessed cells do not interfere with our calculations. The base case is defined for the bottom right corner of the dungeon, where the minimum health required is set to 1. This ensures that the knight survives in the final cell regardless of the dungeon's value at that point. From here, we proceed to fill the DP table, working backward from the bottom right corner towards the top left. For each cell, we calculate the minimum health required to move to the next cell, either to the right or downward, and adjust for the dungeon's value at that position. The math.max function ensures that the health never drops below 1, as the knight must stay alive. After completing the nested loops, the DP table is fully populated with the minimum health required at each cell to reach the destination. The result we are interested in is stored in DP00, which represents the minimum health required to start at the top left corner of the dungeon and successfully reach the bottom right corner. Finally, we return this value as the output of the function. This approach ensures that we account for all possible paths and guarantees the knight's survival while minimizing the initial health required. The dungeon game problem challenges us to determine the minimum initial health a knight must have to travel from the top left corner to the bottom right corner of a dungeon grid. Along the way, each cell either increases the knight's health, decreases it, or leaves it unchanged, and the knight must always have at least one health point to survive. To solve this, we use a dynamic programming approach, calculating the required health backwards from the destination to the starting point. For instance, in the given example dungeon, we begin by initializing the grid dimensions m and n as 3, representing 3 rows and columns. We also create a dynamic programming table filled with infinity to handle boundary conditions, ensuring that calculations for cells outside the valid grid are consistent. This setup forms the foundation for our solution. To set up the base case, we define the health required to exit the dungeon as 1 for both the cell directly below the bottom right corner and directly to its right, represented by DP 3, 2, and DP 2, 3. Starting with the bottom right cell itself, which has a value of -5, the minimum health needed to exit is 1. From this, we calculate the health for this cell as max 1, 1, minus 5, resulting in 6. Moving left through row 2, we calculate the health needed for each cell. For example, the cell with a value of 30 requires only 1 health, as any damage beyond 0 is reduced to the minimum of 1. Similarly, the cell with a value of 10 also requires just 1 health. Continuing upwards, we process row 1. For the cell with a value of 1, the health needed is 5, calculated as max 1, 6 to 1. The cell with a value of -10 requires 11, as the knight needs to offset the damage taken. Finally, the leftmost cell, with a value of -5, requires 6 health. Row 0, the topmost row, is processed similarly. For the rightmost cell, with a value of 3, the knight needs 2 health. For the middle cell, with a value of -3, the required health is 5, and for the leftmost cell, with a value of -2, the required health is 7. After completing the calculations for each cell, we find that the minimum initial health required for the knight to survive the dungeon is given by the top left cell of the DP table, which is 7. This value ensures the knight can safely navigate through each cell while maintaining at least 1 health point. To reinforce the concept, let's consider a simpler example with a single row dungeon. In this configuration, the knight only moves from left to right. Starting with the last cell, which has a value of -5, the required health is calculated as 6. For the middle cell, with a value of 3, the health decreases to 3 because the knight gains health here. Finally, for the leftmost cell in the single row dungeon, which has a value of -2, the required health becomes 5. Thus, the minimum initial health for this scenario is 5, as determined by the first cell of the DP table. Now consider a single column dungeon, where the knight only moves downward. Here, we start from the bottom cell, which has a value of -5. The required health for this cell is 6, ensuring the knight survives the damage. Moving up to the middle cell, which has a value of 3, the required health decreases to 3, accounting for the health gain. For the topmost cell in the single column dungeon, with a value of -2, the required health is 5, ensuring the knight can safely complete his journey. Therefore, the minimum initial health for this dungeon is also 5. These examples illustrate how the dynamic programming approach adapts to different dungeon configurations, always ensuring the knight has enough health to survive. By working backwards from the destination, we systematically calculate the health required for each step, efficiently solving the problem. The time complexity of our solution is O(m*n), where m is the number of rows and n is the number of columns in the dungeon grid. This is because the algorithm uses a dynamic programming approach, systematically iterating over each cell in reverse order, starting from the bottom right and moving to the top left. To break it down, the outer loop runs m times, once for each row, and the inner loop runs n times, once for each column. Within each iteration, the algorithm performs a constant amount of work, specifically calculating the minimum health required to move to the next cell. This means the total number of iterations is the product of m and n, and since each iteration involves constant time computation, the overall time complexity is O(m*n). This efficiency is a major improvement compared to a brute force approach, which would explore all possible paths in the dungeon and result in exponential complexity in the worst case. Now let's discuss the space complexity of the algorithm, which is O(m*n). This is due to the creation of a 2D dynamic programming table, DP, with dimensions m+1 x n+1. The extra row and column are added to simplify boundary conditions by initializing them to infinity. The memory required for this table is proportional to the number of cells, specifically m+1 n+1. However, in asymptotic analysis, these constant additions from the extra row and column are negligible, so the space complexity simplifies to O(m*n). When we break this down further, the main memory consumption comes from the DP table itself, which is O(m*n), while other variables like loop counters and temporary storage add only O(1) to the total. Therefore, the overall space complexity remains O(m*n). The time complexity of the algorithm remains the same in the best, average, and worst cases. This is because the algorithm processes all cells in the dungeon grid exactly once, regardless of the values within the grid. As a result, the time complexity is consistently O(m*n). To put this into perspective, consider a brute force approach. A naive method would explore every possible path from the top left to the bottom right of the grid. For a grid of size mxn, the number of potential paths grows exponentially, approximately O(2)m+n in the worst case. Additionally, for each path, the health requirements would need to be calculated, leading to an overall time complexity of O(2)m+n. The space complexity of such a brute force approach would also be O(m+n), as the recursion stack would store the current path. Clearly, the brute force method is infeasible for larger grids, underscoring the need for the optimized DP solution. The optimized dynamic programming approach significantly outperforms a brute force solution. Its time complexity is O(m*n), an exponential improvement compared to the O(2)m+n of the naive method. The space complexity is also O(m*n) due to the DP table, which is higher than the O(m+n) recursion stack of brute force but still manageable for large grids. To justify this mathematically, each cell in the DP table is filled exactly once, and computing the value for each cell takes O(1) time. This results in a total of m*n(O)(1) operations, simplifying to O(m*n). There are no additional recursive calls or loops beyond the traversal of the DP table, confirming that the time complexity scales linearly with the number of cells in the grid. In summary, the optimized solution achieves linear time complexity relative to the grid size, making it both efficient and scalable for large inputs. The space complexity is similarly linear, and the DP approach is vastly superior to brute force, which suffers from exponential time complexity. One common mistake when solving this problem is not handling edge cases properly. For example, a grid that's only 1 by 1, or one where all the values are negative or positive, can break solutions that rely on assumptions like having multiple rows and columns or mixed values. It's critical to account for these scenarios up front. Another issue is incorrect base cases in recursion. When using recursion to solve the problem, you must clearly define what happens when you reach the bottom right cell, as missing this can lead to infinite recursion or wrong results. Lastly, using brute force without optimization is a frequent pitfall. While it might seem straightforward to explore all paths, this approach results in exponential time complexity, making it infeasible for larger grids. Memoization or other optimizations are essential to handle this effectively. Another key mistake is misinterpreting the problem statement. It's easy to confuse the minimum health required at each cell with the actual health left. This misunderstanding can lead to incorrect calculations and a solution that fails under certain conditions. Additionally, in languages like Java, overlooking integer overflow can become a problem when dealing with large grids or extreme values. Without proper handling, operations might exceed integer limits, causing runtime errors or undefined behavior. Being mindful of these pitfalls ensures your solution is robust and resilient across different scenarios. This problem emphasizes some crucial insights for interviews. First, working backwards from the bottom right cell is essential. By calculating the minimum health required at each step in reverse, you simplify the logic significantly. Second, the optimal approach here is dynamic programming, using a bottom-up method with a DP table to track the minimum health needed for each cell. Third, always consider edge cases like a grid with only one row or column. Bringing up these cases during an interview shows your attention to detail. Lastly, you can optimize space usage by reducing the DP table to a single row or column. This is a common follow-up question that tests your ability to improve efficiency while maintaining correctness. This problem is closely related to other grid-based dynamic programming challenges. For instance, LeetCode 64, minimum path sum, involves a similar traversal approach but focuses on calculating the sum instead of health requirements. Another related problem is LeetCode 62, unique paths, which counts the number of paths in a grid and shares overlapping DP concepts. A variation of this is LeetCode 63, unique paths 2, where obstacles add an extra layer of complexity, requiring careful handling of edge cases. Lastly, LeetCode 221, maximal square, is another DP-based grid problem, but it focuses on determining the largest square that can be formed, emphasizing precise state transitions in edge case management. There are multiple approaches to solving this problem, each with its trade-offs. Brute force involves exploring all possible paths recursively. While simple to implement, it's highly inefficient due to its exponential time complexity. A better approach is top-down dynamic programming with memoization, which stores intermediate results to avoid redundant computations. However, this requires additional space for the memoization table. The bottom-up DP method builds the solution iteratively, starting from the bottom right cell, and is generally more space-efficient. Finally, space-optimized DP takes this a step further, reducing the DP table to just a single row or column. While this achieves optimal space complexity, it requires careful implementation to ensure correctness. Great job! Today, we explored an efficient approach to solving the dungeon game problem using dynamic programming. Remember, mastering such problems takes time and consistent practice. Thanks for tuning in. Don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!